All right, you guys, time to take a look at lesson 67. Lesson 67, where we're going to solve and classify special systems of linear equations. Now, before we do this, I would like to check your warm-up with you. The warm-up is important today, that we remember how to do especially numbers 2, 3, 4, and 5. But just for good measure, the answer to number 1, the blank that needs to be, the word that goes in the blank there, the word is system. Did anybody get that word right? I would be so impressed. That's a tricky one to remember, that a system of linear equations is a set of linear equations with the same variables. That's what we call a system of equations. Now for number 2, 3, 4, and 5, we have a few equations here, and we're supposed to determine the slope and the y-intercept. For number 2, our equation is in y equals mx plus b form. It was y equals 4x minus 7. For this one, in order to find m, the slope, and b, since it's already in the form y equals mx plus b, we just have to identify where m is, which is right here, so the slope is 4, and the y-intercept is this constant right here, negative 7. Okay, so we know that that line is going to intersect the y-axis at negative 7. For number 3, we're going to have to move some variables around. Okay, so we have 6x minus 2y equals 18. Again, I'm trying to solve for m and for b, but I need this equation in the y equals mx plus b format. So I'm going to move this 6x over here to this side. So I get it off of here, and I end up with negative 2y equals, and now again, because I want it in y equals mx plus b, I'm going to put the x's first. Negative 6x, 18 is positive, not quite finished. It needs to be y by itself, and it needs to be a positive y, which means I need to divide by negative 2, and I need to divide every single term by negative 2. Doing that, I end up with y equals negative 6 divided by negative 2 is positive 3, x. 18 divided by negative 2 is minus 9. I'm now in y equals mx plus b form, so I see clearly y equals m. There's the slope. M is 3. X, b is the negative 9. That's the y-intercept. Okay, all right, number 4. Find the slope of a line parallel to 15x plus 3y equals 24. Trick to this is that we have to remember that parallel lines have the same slope. So when I convert this into y equals mx plus b form, the m, the slope, that's all they're really asking me to find, right? Is what is the slope of this line, because any line parallel to this line has to share the same slope. So let's move the 15x from this side to this side. And I'll have 3y equals, again, I want my x's to lead, negative 15x, 24 is positive. They're not like terms, so I can't combine them, right? I'm just trying to visualize how this is going to work. I divide by 3, I divide every single term by 3, and I get y equals negative 5x plus 8. The slope of this line is negative 5. Y equals mx plus b. M is the slope. So any line parallel must have the same slope. That's what defines a parallel line. Now for number 5, you got to reach back there into your memory and remember that they're asking us now to find the slope of a perpendicular line to this equation. X plus 4y equals 7. Slopes between perpendicular lines, you remember how this works? They must be negative reciprocals. So first things first, I've got to find out what the slope of this line is before I can determine what its negative reciprocal is. So I'm going to move the x over here, and I'm going to move it over here. It gets rid of it on this side, and I have 4y equals, I'm going to lead with the x, negative x, don't combine these, you can't, plus 7. Okay? Divide every term by 4, and I will end up with y equals negative 1/4 x. That's what you needed to see here. That the implied slope here, before the x, is a negative 1/4 x plus 7/4. Okay? So, the negative reciprocal of my slope, what is the negative reciprocal of negative 1/4? Well, the reciprocal is 4/1, and if I flip that sign, it's going to be just plain old 4. So the slope of a perpendicular line to this equation must be 4. All right, let's go ahead and put whiteboards away, and we are going to move into lesson 67. So this is a good place to press pause, reset, and then we will get started. All right, if we've got everything we need on our desks, a pencil, you might want a calculator for today. You might possibly want a colored pencil, but again, that's up to you. Our lesson today, solving and classifying special systems of linear equations, might be tricky because it has some new terminology, some new words for us to learn, but it also might not be tricky because there really are absolutely no new concepts here for us to learn. We just need to learn the vocabulary. That's what it means to classify special systems of linear equations. We've already learned about these linear equations, but we haven't learned yet that they have special names, special classifications. So that's what we're going to learn about today. The first type or classification of systems of linear equations that we're going to learn about today are called, in fact here, I'll use my orange pencil, are classified as inconsistent equations. Okay? Inconsistent equations. When we have two equations that are classified as inconsistent, what that means is that no common solution exists. That means that those two graphs, those two lines, right, because we're dealing with linear equations, never intersect. They never have a point where both of them are true at the same time, which means because we have two lines that never intersect, that we're dealing with parallel lines, okay? Parallel lines. We have to remember parallel lines have the same slope, remember, but a different y-intercept. If that is what we've got between two equations, then what we have before us is called an inconsistent system. In an inconsistent system, again, there are no solutions that will satisfy both equations. Here's an example. The first equation is y equals 5x plus 6. Our second equation is y equals 5x. We can see immediately that these two things will never be true at the same time. But we can prove it through substitution. Because we have y equals 5x, okay, we could take this 5x right here and substitute it in for y. Because our equations are telling us that this y is the same as 5x, which would look like this. 5x equals this part. 5x plus 6. Now, if I were to try to remove 5x from this side and move it over here, subtract it from this side, I would end up with 0 equals 6. That is a false statement. And because it is false, okay, here's the way we would write the answer. 0 does not equal 6, so there is no solution. It is what we call an inconsistent system, right here. Okay? An inconsistent system. Now, we could do the same. This is just a second example for us to see y equals 1/2 x plus 1/2 and y equals 1/2 x plus 7. Here I can see immediately they have the same slope. These are in the form, the slope-intercept form, y equals mx plus b. I can see m is the same for both. Okay, they both have the same slopes. They're parallel lines. This one's going to hit the y-axis at 1/2. This one's going to hit the y-axis at 7. They are not going to intersect, but I can prove it through substitution. Okay, so if I set, because y equals this and y equals this, according to these, they should equal each other. Let's see if that is true. 1/2 x plus 1/2 equals 1/2 x plus 7. We know immediately, just looking at this, that this is going to be a false statement, right? Because if I move the 1/2 x here, and I remove it over here, I've got to subtract it from both sides, which ends up being 0, okay? And I subtract 1/2 from this side, and I subtract 1/2 from here, I'll end up with 0 on that side of the equation, equals 6.5. Not true. So these two equations represent an inconsistent system. Okay? So we've worked with this before, we understand this, but today we're just learning the words to describe what's happening. So parallel lines represent an inconsistent system. Now, we have two types of consistent systems, okay? And it looks like you've got, okay. We'll have to look here and see how Mrs. Fairbank arranged your notes. Oh, here we go. On the next page of your notes, if you see consistent system, so here's our inconsistent system. Parallel lines, and what happens in the math when we try to solve a system of equations and it ends up being a false statement, there's no solution, is we understand that we're looking at parallel lines. Consistent equations, okay, or consistent systems, two separate lines, can be expressed in two different ways. We have independent consistent systems and dependent consistent systems. Let's start with dependent systems, okay? So we've just moved from inconsistent systems to consistent systems, and there are two types. The first type of consistent systems is called a dependent system. A dependent system has an infinite number of solutions. Infinite number of solutions, all right? So equations of a dependent system are called dependent equations, meaning they have identical solution sets. If two equations end up being identical when you do the math and the two sides end up equal to each other, what you have is the same exact line, okay? If we've got infinite solutions or infinite set of ordered pairs that satisfy both equations, then what you're looking at is two forms, right? Two different forms of an equation that represent the exact same line. Let me show you how we can figure this out. Two different methods for this, all right? So we've got our two equations right here, and one way we can prove that this is a dependent system, meaning it has infinite solutions, is that I can show that when I write both of these equations in slope-intercept form, they're going to be identical. Watch this. Okay, so x minus 4y equals 8. I'm going to write that in y equals mx plus b form. So first thing I'm going to do is move the x. I'm going to end up with negative 4y equals negative x. Remember, I can't combine these. These aren't like terms, so I have to list them separately. Minus x plus 8. Divide by negative 4 to get y by itself. Divide this by negative 4. Divide this by negative 4. And I'm going to end up with y equals, remember there's a 1 here, right? Okay, 1/4 x minus 2. Great. Let's take a look at the second equation. Okay, here's my second equation. 1/4 x minus y equals 2. I'm going to subtract the 1/4 x from this side and move it over here, like this, 1/4 x, and I'll end up with minus y equals negative 1/4 x plus 2. I need a positive y, so I'm going to divide everything by negative 1, okay, which is essentially just going to change the signs. So I'll end up with y equals 1/4 x minus 2, because I needed to change the side. I just multiplied everything by, divided everything by negative 1 to get a positive y. I just proved that when I rewrote these two equations in y equals mx plus b form, they are identical. That means they have infinite solutions and they're classified as a dependent system. They're the same line. The equations are identical. So they have infinitely many solutions. Okay? That's called a dependent system. Now we could prove it a second way. We could prove it through substitution. All right, so in using this method, we're going to isolate y in the second equation. It's got to be a positive y. Okay, and then substitute it into the first equation. Okay, let's do this one step at a time. Here's our second equation. 1/4 x minus y equals 2. And it says I need to isolate it, right? So I'm trying to get it in the form of y equals, which I already did. Remember, I did that up here. Okay, so let's just take the work that we just did. Once you do all the work, you're going to end up with y equals 1/4 x minus 2. Once I move all that stuff around, I'm going to end up with y equals 1/4 x minus 2. Now, because y equals 1/4 x minus 2, I can take this whole thing and I can substitute it back into my first equation. The first equation was back here, and it was x minus 4y equals 8. Y equals this whole mess right here. Okay, so if I substitute that back in, minus 4, and I put it in here, 1/4 x minus 2, okay, because I'm substituting this value in here for y. I set the whole thing equal to 8. I do my distribution. X, let's distribute, minus 4 times 1/4 x here, right, is just going to be, this is going to end up being minus 4 over 4, which is negative 1, which is negative x. Minus 4 times minus 2 is plus 8, equals 8. X minus x, these guys are out of here, and I get 8 equals 8. When I have that truth value statement, 8 equals 8, that tells me that there are infinite solutions, right? Infinite solutions means I'm dealing with a dependent system. Okay, so I've got infinite solutions, which means I have a dependent. Dependent has all E's in it, in case you're wondering, okay? No A's. A dependent system. Okay? Infinitely many solutions, any ordered pair satisfies y equals 1/4 x equals 2. I think this is supposed to be a minus. I think that's a typo. In any case, either one of these methods, method 1 or method 2, will, as long as we end up either with identical equations or exactly the same number on either side of that equals, we know that we have not only a consistent system, but this kind of consistent system, a dependent consistent system. Now there is one other type of consistent system that's not a dependent system, but an independent system. Okay? An independent system. Now, that's not what we're going to see right here, actually. Here, I think we're going to see, well, let's figure it out. Before I explain to you what an independent system is, I guess you could see it here in the graphs. Okay, so far we've seen this one. Inconsistent system, where there are no solutions, they never intersect. Same slope, different y-intercept, they're parallel lines. That's called an inconsistent system. They'll never have a point on either one of those lines that's going to be the same. The one that we just looked at is a consistent system, this type, a dependent system, where we saw the equations were the same or the number on either side of the equal sign was the same. In essence, it's the same line and has infinitely many solutions. There's one other type of consistent system called an independent system. An independent system has only one solution, and it is the point at which two lines intersect. Okay? That is still a consistent system because it can be solved. There is a place where those two lines will share a solution, but they only share one. So let's look at this one here. This is going to be a consistent. I'll just give you that hint. This is going to be a consistent system, okay? Now, is it going to be dependent or independent? Let's solve it and figure it out, okay? So I'm going to write both of these equations in terms of y. I think that might be easiest for me. So I'm going to move this x over here, and I'm going to move it over here. It moves it from this side, and I get y equals negative x plus 10. Okay? I'm going to rewrite this equation in terms of y, so I'm going to add x over here. I'm going to add x over here, and I get negative y equals x minus 10. Now remember, I don't want a negative y. I want a positive y, so I'm going to flip every sign by multiplying by negative 1, right? So y equals negative x plus 10. Both of these equations, when they were written in terms of y, produced the exact same variables and constants in the same order. So I get x plus 10, because y equals that here, and negative x plus 10. This one, when it was rewritten this exact same way, negative x plus 10. So if I add x here to move it, and I add x over here, I end up with 10 equals 10. Okay, I've got the same number on both sides of the equation, so I know it's a consistent system, but which one is it? Independent with only one solution, or dependent with infinitely many solutions? And the answer is dependent. It's the same line. Remember, I've got both things on the same, both values are equal on either side of that equal sign. The equations are identical, and so what I have is a dependent system of equations. Same line. All right, guys. Just a few more to classify here, and then we'll be done with this lesson for today. So our job here, okay, we'll have these three, and then we've got one application question to work through. Okay. Our job is to determine if each system of equations is consistent and independent. Okay, that's this one solution. Consistent and dependent, that's this one. Every single value is exactly the same, so same line. Or inconsistent, same slope, different y-intercept. Okay, so let's go ahead and do them one at a time. X minus 7y equals 3. All right, so I'm going to go ahead and solve this in terms of x, and then I'm going to take whatever I get there for x, and I'm going to stick it in here and see what I get. All right, so x plus 7, I'm going to move this 7y over here, and I'm going to add it over here, and I'm going to get x equals 7y plus 3. Now, because I know x equals this whole thing, I can take this and substitute it in for x. And I get 2 times 7y plus 3 minus 5y equals 15. Distribute. Okay, I'm going to distribute to this term first, and then I'll distribute to the second term before I move on to do any of the addition or subtraction. 2 times 7y is 14y. 2 times plus 3 is plus 6, minus 5y equals 15. Let's combine like terms. I've got 14y minus 5y. Okay, so 14y minus 5y is going to give me 9y plus 6 equals 15. Subtract the 6 here, and I'm going to end up with 9y equals 9, and y equals 1. Okay, so I'm solving this system of equations here. So I've got y equals 1. What is x? Okay, what is x? So if I've got y equals 1, I'm going to go ahead and put y equals 1 back into one of these equations. I think I'm going to, I'll stick with the first one. Okay, remember to put it in the equation before we did any manipulation to it. So x minus 7 times 1 equals 3. X minus 7 equals 3. Add 7. Add 7, gets rid of it here, and x equals 10. So I have a solution set. The solution set is 10, 1. How many solutions did I just come up with? Okay, I did come up with a solution. So I know it's not this one. It's not the inconsistent one. I didn't come up with infinite solutions. I came up with a single solution where x equals 10 and y equals 1. These two equations are satisfied, which means this is a consistent, independent system. Okay? All right. 2 more to go. 2 more to go. Oh, I like this one. I like this one because it's already written in terms of a single variable here. So I already can see that y equals 4x minus 5. So I'm going to take this whole thing and I'm going to substitute it in here for y. Okay, so that I can see if I can solve this system of equations. So 8x minus 5 times, instead of putting y here, I'm going to put what it equals, which is 4x minus 5. equals 16. Do the distribution before you do combine any kind of like terms. So multiply here and multiply here. Remember that this is a negative 5. Here we go. 8x minus 5 times 4x is minus 20x. Minus 5 times minus 5 is plus 25 equals 16. 8x minus 20x, okay, is going to be negative 16x when I move the 25, subtract 25 from here, and I subtract 25 from here. I am, there we go, okay, I'm going to get negative 16x. Did I do that right, guys? Or did I mess that up again? Let's see. Hold on a second. Oh, gosh. I'm sure somebody caught that, right? 8x minus 20x wasn't 16x, for goodness sake. It was 12. Okay, there we go. That looks better. Negative 12x equals, because 16 minus 25 is, guess what? Negative 12. Oh, excuse me, negative 9, right? Negative 9, there. And I'm going to divide by negative 12. And end up with x equals 9/12, which I can reduce to 3/4. Whew, good. Glad we made it through that one. All right, x equals 3/4. Now I need to find a solution for y, okay? I need to see if there's a solution for y. So if I take 3/4 and I put it back into one of these equations, I think I'm going to go ahead and use this one right here. Y equals 4. This is my x value times 3/4 minus 5. I get y equals 3 minus 5. Y equals negative 2. Okay? So my solution set is x and then y, remember? 3/4 and then 2. Now that I've done all that, I still haven't answered the question. The question is determine if the system of equations is consistent and independent. Consistent and dependent, that means they have all of the solutions in common, or inconsistent, they have no solutions. Well, in this case, I had exactly one solution, which means it's a consistent and independent system, just like the one above it. All right, so the answer to letter B is consistent, independent, because it has one answer, system. Consistent and independent system. Okay, one last set of equations to go. Here we go. I've got 4y equals 4x plus 4, and negative 4y equals negative 4x minus 4. I hope that you're seeing what's happening here. Okay, if I were to multiply one of these equations, if I were to multiply either one of them by negative 1, okay, let's just multiply this one by negative 1. I would end up with, as long as I multiply every single term that keeps those proportions consistent, then I'm okay. So I've got negative 4y equals negative 4x minus 4. Now check it out. Here's my second equation. Negative 4y equals negative 4x minus 4. What happened? I ended up with identical equations, which means I know immediately that I'm dealing with this right here, a consistent, dependent system. Same line, infinite number of solutions, and I knew it because I've got the same equation. Okay, the same equation. Now, if I were to combine these, that's one way to do that. Let's say I were to take these and I were to try to add them together. I'm not going to multiply. With this one, I multiplied this whole thing by negative 1, right? I saw that they were the same. I could have also done it this way. Let's take this equation right here. 4y equals 4x plus 4. And I can solve that by adding them together. So if I add the other equation with it, negative 4y equals negative 4x plus 4. Okay, then I'm going to end up here with my, why did she do it this way? This is going to put 0 and 0 and 4. Yeah, I don't know why this particular, guys, this was in your notes this way. Just cross this out.